What if I have binomial data from two different samples that are from two potentially different populations? Like, for instance, I get data from a controlled experiment. I have my control group and my test group. I do something to them. I measure some result. I get binomial data, a yes or a no from each element of my samples. And I want to know, I get a difference, but I want to know, is this difference statistically significant? This is what we're going to do right now. We're going to learn how to do a hypothesis test and a confidence interval to study a potential difference between two different samples. Let's do a for instance. Suppose 193 students are taking the final exam in introductory biology. On the final exam, we ask all students to state their principal method of note-taking. We want to know if it makes a difference how you take your notes. We find that 127 students reported using pencil and paper, and of these students, 74 of them scored an A or a B on the test. We find that 66 students reported using a computer for their note-taking, and of these, 31 scored an A or a B. First question, is this a controlled experiment? This is not a controlled experiment because we didn't randomly divide our sample into groups and treat them differently. We did not assign which students are going to take notes with pencil and paper and which students are going to take notes on the computer. We didn't tell them that. They made their own choices, and then we just measured the results. So as a result, this is a survey type of study. This is an observational study. This is not a controlled experiment. As a result, if we do find a difference, suppose if there's a statistically significant difference here, this is only going to tell us that we've got a correlation, an association between note-taking method and final grade. We can't conclude that one thing causes the other. We cannot conclude causation here because, well, for a survey observational study, there are always confounding factors. In this case, I don't know, maybe students who invest money in a nice computer to take notes on also invest more time in studying. There's a million different ways these things could be interrelated with each other. The only way to know whether one thing causes the other, the only way we could get evidence that a particular note-taking method causes an increase in grades is if we do a controlled experiment. If we randomly select one group of students to take notes this way and another group of students to take notes that way, and then if we measure a difference, and it's a statistically significant difference, then and only then can we really conclude that there is a cause-effect relationship here. So what's the first thing to do? We need to make some point estimates. All right, first taking a look at the students who did notes with pencil and paper. Our p-hat is 74 out of 127 students, which is 0.583 or 58.3%. Of the students who took notes with the computer, our p-hat is 31 out of 66 students getting an A or a B. That gives us 0.470 or 47%. So we have a difference here. 58.3% minus 47.0% is 11.3%. The students who took notes pencil and paper did 11.3% better than the students who took notes on a computer. But that doesn't necessarily mean anything. We're not done here because, well, this is just a sample. This could have happened by random chance. If we did this study again, if someone else did this study again, they would get different results. They would probably not get exactly 11.3%. They might get something bigger. They might get something smaller. It could be that the real difference, again, if we did this with very large samples to do the whole population, perhaps we get no difference at all. So we need to do math. We need to figure out whether is that difference of 11.3% statistically significant. So the first thing we want to do is do a hypothesis test. So here are our hypotheses. The null hypothesis, when I've got two samples, the null hypothesis is almost always that there's no real difference here. The only difference is just due to, randomness and gathering our sample. The null hypothesis would say, in this case, it doesn't make any difference one way or another, whether you take your notes on a computer or on pencil and paper, the average proportion of students who get an A or a B is going to be the same either way. So again, remember, this is a statement about the populations in question, not the sample. So the null and alternative hypotheses are always statements about P, not p-hats. So for our alternative hypothesis, again, in general, there are three possibilities. Our alternative hypothesis could be that the computer takers get a higher proportion than the pencil and paper takers, or vice versa, or that there's simply a difference between here. If there's simply a difference between here, that would be a two-sided alternative hypothesis. In this case, the logical thing to choose is just that there's simply a difference. It would be interesting to us if the difference went one way or another way. If it's better to take notes on computer, I want to know that. If it's better to take notes on pencil and paper, I want to know that too. Both of those would be meaningful, interesting, important results for me. So anything other than there's no difference at all would be useful to us. And so as a result, we choose the alternative hypothesis of that these two proportions are simply not equal to each other. So we'll do a two-sided test. Now, the next thing we need to ask ourselves is, can we use the z-distribution? Can we use the normal distribution? The normal approximation to the binomial distribution? It makes the math a whole lot easier. Let's check. First of all, our sample sizes are both more than 30. The number of pencil and paper users were 127. Computer users were 66. No problem there. We also need to double check that we've got at least 10 in each category. And in this case, we got 74 people got A's and B's in the pencil and paper group. And 127 minus 74 is 53 people getting other grades. That's fine. Both 74 and 53 are larger than 10. Similarly, in the computer note-taking sample, 31 of these people got A and B grades. 66 minus 31 leave 35 people getting other grades. Great. 35, 31, 53, and 74, all four of those numbers are larger than 10. So we're golden. We're good to go here. We can use all the standard formulas for the normal approximation to the binomial. Now, the logic of a hypothesis test is we assume that the null hypothesis is true. There's no real difference here. Any difference we got was just due to random chance. And then we calculate, all right, if Mr. Null hypothesis is true, what's the probability we're going to get a difference this large, 11.3% or larger, just by random chance? If that p-value is really unlikely, we reject the null. For this test, let's choose a significance level of alpha of 0.01. 1% is going to be our threshold at which we'll reject the null hypothesis. Okay, if we're going to do this, we need to pool our data together to get our standard error. So again, the null hypothesis says note-taking method doesn't affect test scores. These are all these two samplers are really samples from the same population. So therefore, it makes sense to just put our data all into one big giant pile. In the numerator, we add up all the students who got A's or B's, 74 in the one group, 31 in the other group, and then the denominator, here's all the students who are in our study, the 127 in the one group plus 66 in the other group. We add all that up and we get 54.4% of all the students got A's or B's. Step one, we use this to calculate our standard error on the difference in proportions between our samples. So here's a great big giant amazing magical equation, which will do this. We put p hat pooled, that 0.544 into there, and we divide behind the different sample sizes. So what do we got? We have the square root of 0.544 times 1 minus 0.544 divided by 127 plus 0.544 times 1 minus 0.544 divided by 66, square root of that whole thing, and we have a standard error on the difference in these proportions of 0.0756, 7.5% standard error. The next thing we need to do our hypothesis test is compute our test statistic, our z-value, to measure that difference that we got, that 11.3% difference. How big is that in terms of standard errors? How many standard deviation big is that? So we take our 0.583 minus the 0.470 to get our difference of 11%. We then divide that by our pooled standard error of 0.0756, and we get a z-value of 1.49. We are 1.49 standard deviations away from no difference at all, which is where the null hypothesis says we should be. Remember, the idea of the null hypothesis is it says that there's no real difference here, and that if you were to do this test again, you're just as likely to get a higher proportion of A's and B's among the computer note takers as among the pencil and paper takers. So half the time you'll get a positive z-value, half the time you get a negative z-value. The only differences that happen are just due to random chance and randomly gathering our sample from the population. So now we need to compute, is this likely? Is it likely to get stuff like a z-value of 1.49, a difference as big as 11.3%? If there really is no underlying difference here, we evaluate this by computing our p-value. That is the probability that we would get a difference this big or bigger, assuming that we had got a test statistic a test statistic of 1.49 or more, assuming that the null hypothesis is true. So in this case, we're doing a two-sided test. Remember, I would be just as interested if it was better to take notes on the computer as it would be with pencil and paper. So we're going to need to do a two-sided test, see both tails of this. In this case, I have a positive z-value, positive 1.49, and I want the tail, not the body. So I do 1 minus p norm of 1.49. I want the probability of getting 1.49 or more. So I do 1 minus 1 p norm of 1.49, and I get 0.068. And there's a 6.8% chance of getting something like that. This is a two-sided alternative hypothesis. I would have been just as interested if I got negative 1.49 or smaller. So to include both tails, the probability of getting a difference this big or bigger in either the positive or the negative sense, we multiply this by 2, and yeah, so 2 times 0.068 is 0.136. That means there's a 13.6% chance of getting a difference this big or even bigger in either the positive or the negative sense. So what do we conclude? What's the results of our hypothesis test? Well, in this case, our p-value is larger than alpha. We said that our alpha was going to be 1%. That was our threshold of unlikeliness for calling, rejecting the null hypothesis. In this case, we got more than 13%. So what do we conclude? Well, based on this, we say a difference of 11.3%. That's not a very unlikely result. If there was no underlying difference here, that should be a relatively typical, commonplace. That's the sort of result we would expect to happen all the time, just as a result of random variation. So we fail to reject the null hypothesis, or in other words, our difference of 11.3% is not statistically significant. Those phrases mean the same thing. Fail to reject the null hypothesis, not statistically significant. So what does that mean? What conclusions can we draw? Nothing whatsoever. We learn nothing. Whenever we fail to reject the null hypothesis, we learn nothing at all. We can draw no conclusions about whether or not there's any correlation between note-taking method and exam grades. Here's a really important idea. We never, under any circumstances, ever accept the null hypothesis. Ever. That does not happen because we didn't find a difference. Just because you don't find something doesn't mean it's not there. We can't conclude that note-taking method doesn't matter. It's possible that note-taking method matters. It's possible that taking notes on pencil and paper really is better than taking notes on a computer, or vice versa. It's just that this data does not allow us to draw that conclusion. This difference we got wasn't big enough to draw that conclusion. This study didn't find a difference. Some people, here's another example. NASA would love to know if there's life on Mars, if there are little microbes, bacteria running around on Mars somewhere. They've spent the last 20 years sending our little RC cars to drive around on Mars and look for microbes on Mars. They haven't found anything. Does that mean that there's no life on Mars? Does that prove there's no life on Mars? No, not even close. It just means we haven't found it yet. It could be that Mars is sterile and there's no life there, or it could also be that we just haven't looked in the right places yet. Mars is big. It's a whole planet. We've only looked in a relatively small number of places. That's what's going on. That's the same sort of logic that's going on when we fail to reject the null hypothesis, when we don't find a statistically significant difference. It doesn't mean there's no difference there. It just means that this data didn't find a difference. So what's the next thing to do? Well, okay, we've completed a hypothesis test. Now, more interestingly, let's make a confidence interval. Well, let's see. We set alpha of being 1% before, so let's make the corresponding confidence interval. Let's make a 99% confidence interval. We're going to create a range that we are 99% confident will contain the population difference between students who take notes with computer versus pencil and paper in terms of the proportions getting A's and B's. This interval will be centered on our best guess. That's 11.3%. That's the difference we got between our two samples. And then we got to put a margin of error on that. We're going to add and subtract something to the 11.3% to account for the uncertainty that comes from these random samples. Step 1, we calculate the standard error based on the samples, and notice that this is a different standard error expression. We calculate standard error in a different way if we're going to do a hypothesis test versus if we're going to make a confidence interval, because the hypothesis test is based on the assumption there is no difference, so therefore we lump all the data together into one pool and we do our pooled standard error estimate. Here, We're just making a confidence interval. We have no idea what the difference between these things is. We're making no assumptions about whether the difference is 0 or anything else. We're just saying, what's the best I can do with this data? So as a result, we do not lump things together. Instead, we take our two things and we deal with them separately. So in this case, we take the square root of 0.583 and times 1 minus 0.583 over the 127. That gives us the standard error part from the people taking pencil and paper notes. And then we add to that 0.470 times 1 minus 0.470 divided by 66. That gives us the variation that comes from the people who are taking notes on computer. We add those two things, take the square root of the whole thing, and we get 0.0754. That's the standard error. That's the standard deviation we would expect to result from if we did this study many, many times with many different groups, we would expect our results, our differences between these two proportions to vary by with a standard deviation of about 7.5%. Step 2, well, we need to find our critical value based on our confidence level of 99%. So here's the logic again. We want a 99% confidence interval, so I want to capture 99% of the normal distribution inside my interval, and I want to leave 1% outside of the interval. So I want to leave a 0.5% on the positive side, 0.5% on the negative side. So I go to my good friend R to calculate my Z star value, my critical Z value. I go to Q norm. I can do this with 0.995, leaving 0.5% in the right tail and 99.5% to the left of this, or I can do this with negative of Q norm of 0.005, now putting 0.005, 0.5% in the left tail, and since the normal distribution is symmetrical, it's the same thing to the right and to the left. Both give me the exact same number, which in this case is 2.58. To get the margin of error, we multiply these two things together. We multiply our critical Z value, 2.58, times our standard error, which was the 7.5%, and we get 0.194. We got about a 19% margin of error on this to get a 99% confidence interval. We then add and subtract this to the difference we got. The proportion of A's and B's among the pencil and paper note takers, the proportion of A's and B's among the computer note takers. So there's the 0.583 minus the 0.470, giving me my 0.113, the 11.3% difference. And then I add and subtract 19%, 19.4% to that. And so my confidence interval ranges all the way from negative 8.5% all the way up to positive 30.7%. So again, calculating a confidence interval is important. Even more important is to being able to correctly interpret it, being able to explain and understand exactly what that means and what it doesn't mean. Based on this data, to interpret this confidence interval, we are 99% confident that the true population differences in the proportion of students who get A's and B's in the final exam between students who take notes with pencil and paper and those who take notes on a computer is between negative 8.1%, meaning the computer note takers would do better, and positive 30.7%, meaning on that side the pencil and paper note takers would do better. Now notice that this interval, that includes 0. We have both negative and positive numbers, so as a result, we cannot rule out the possibility of 0 difference, no difference at all. We cannot reject the null hypothesis. Hey, that's what we found in our hypothesis test, so there's not a coincidence. We have to get the same result both ways. Now, note, on the other hand, that I think we learn more from doing the confidence interval than we did from the hypothesis test. The hypothesis test ends with a conclusion. Reject the null hypothesis or fail to reject the null hypothesis. Nothing else. So all the hypothesis test told us was that the difference could be 0. There might be no difference there. On the other hand, this thing tells us a whole lot more than that. For instance, this confidence interval tells us we could rule out a difference favoring pencil and paper of more than 30.7%. That's interesting. It says if pencil and paper is better, it's not going to be more than about 30% better. You're not going to have, twice as many A's and B's among your pencil and paper group. That's an interesting thing. Similarly, I conclude that If taking notes on the computer is better, the difference isn't going to be more than 8% or so. You're never going to have, 20 or 30% more A's and B's among the computer note takers as opposed to the pencil and paper note takers. It says the difference between these two has got to be pinned somewhere in that range. So when I'm writing an academic paper for publication, I think the most useful thing I can present is a confidence interval like this. Even though in this case we can't rule out the null hypothesis, this tells us something about the differences that are likely and reasonable to happen based on this data, and then what differences are not likely and reasonable. All right, quick summary. What did we do? We compared two samples of binomial data by doing a hypothesis test and making a confidence interval. The null hypothesis in these cases is generally that there's no difference in these population proportions. They're the same thing. They're sampling the same population. The most important thing I want to emphasize on this part of maybe the trickiest thing is that we have different standard errors to do the hypothesis test and to make the confidence interval. While we're doing the hypothesis test, we pool everything together, combining the successes from both groups and the numbers of both groups to get this p-hat pooled thingy, and then we use that to get our pooled standard deviation. On the other hand, when we're making a confidence interval, we don't pool things together and we handle those separately. So we have different equations to draw those, to calculate those different standard errors.